That would be,
Yeah, okay, we are good. Yes, we have a test coming up, right? Our test is next week. It's on Wednesday. So on this Wednesday, just so you know, I'm going to have my biannual means every 2 years. My biannual faculty observation. So the chair of the math department is going to come in here and sit down and watch the lecture. So you behave however you want to behave. I'm just letting y'all know they'll be here. I know some instructors are like, they'll totally change the class. It'll be like students will be sitting like, who the heck is this? Where have they been all? I'm gonna do the same thing I always do. All right. But I actually requested that they come in on the day that we cover the hardest thing that we cover, really. And so it was intentional because I wanted them to actually kind of see the hard stuff instead of me just doing product rule or something simple. Simple, easy. Easier. Common sense stuff, yeah. So just be ready. They may stay the whole class. They may stay for 10 minutes and leave, just so you know that's who they are. All right, so we're going to do today implicit, right? I just want to kind of recap. Today we're going to do implicit differentiation, which we started last week, right? Yep. We'll finish it up. And then on Wednesday, we will do related rates. Please watch the videos, the course videos for 2-7. Because what I'm going to do when I come in on Wednesdays, I'm going to start doing those examples. And if you have no idea the background on the examples, then you're going to be like, well, what's going on? So watch the video. It's like 30 minutes. I know it's a little dry, but when I'm sitting here talking about, okay, we've got that circle that has a radius that's expanding at a constant rate, and you're like, what circle? All right, so just get acquainted with the problems first. And then on Monday, we'll do more related rates. More of that. And then on Wednesday, we have exam 2. Okay? Exam 2 should cover everything that we've done after exam 1. So up through 2.7 or 2.7. All right. Any questions? Let me turn my phone off here.
what's going on Monday?
The same thing, related rates.
I think I'm just when to use the product rule versus the chain rule.
I think the chain rule is...
Well, the main thing is product rule is going to be used when you have multiplication between two functions, and the chain rule is when you have a function inside of another function. So you have to be able to identify the difference between a product and composition. Like on the quiz problem, there was that one that was something raised to the -4. That was composition. That's a function in a function. So
you always do the product first, and then if it's composition, why?
Well, every problem's different. Sometimes you'll have a product that has the composition, and then sometimes you have composition with a product. For example, if you have something like this, versus something like this, all right, that just gives you an example of two things where this one would be a product first, right? So you would do your product rule, and when you do derivative of this one, it's 2x then times this, plus derivative of this would be a chain rule, because you have cosine inside of sine, right? And then you would have to finish off your product rule by multiplying times this. This one, you have composition first. See, the product rule is inside the sign. So you'd have to do chain followed by product. You look like you're just agreeing.
Yeah, well, let's see here.
I mean, I can work these out.
Well, because that's where you use the sign of your hand, right?
Yes, Yeah, that first one would be derivative of sine of something. Would be cosine of the something, right?
Now the derivative of the inside is the product, right?
Now you have a product rule. So we would do the product. Now one thing I did notice a lot of you, not a lot, but quite a few students forget about this, is when you do the product rule here on this inside piece, you do derivative of this one, which is 2x times cosine x plus the derivative of cosine x times the first one, right? That's your product rule on here. That's what a lot of students would put down, and that's not correct because you're missing the parentheses. See, you're saying it's this times that, right? And it's times the whole thing. No parentheses there is a big deal. It's not a little, oh, just parentheses. It's a big deal because I was talking to a colleague of mine about this morning. Like, I was asking them, how many points do you take off when your students leave off this parenthesis? And we both agreed, like, out of 10 points, this is like -2. You know, that's automatically like an 80% because it's that important. And just look at this here. If I write 4 times 5 plus 2, right? I have something times 2 terms, right? Here, something times 2 different terms, yes? That is very different than that, right?
Oh, yeah.
Huge difference. And so that parentheses is not optional just because we like parentheses. It's because it has to be there. So this is what we have here. You must include the parentheses. So on your quizzes, I probably put them there and took off like -1 or -2 if you forgot them. Okay, now the second one here, we would do product rule first. So I would do derivative of the first one, which is 2x, times the second one, right? Yep. Plus, now the derivative of this one. So that's sine of my hand, so derivative of sine of my hand would be cosine of my hand, something like that. So it'd be cosine of what?
So you're doing a product rule within a product rule?
No, I'm doing a product rule. Derivative of this one is 2x times the second one, plus when I do the derivative of the second one, that's a chain rule, right? So derivative of that is cosine of x. Then continuing the chain rule, I just took the derivative of sine of something. Now I have to take derivative of what's here. So now times sine x. Yes, negative sine x. Thank you. And then I'm done?
Well, times the x.
Times the x squared because you have to finish off the product rule, right? Because this part right here is just us saying the derivative of the second one. Now we have to say times the first. You see the difference between those two?
Yeah.
And that's just something you have to get used to, you know, looking at it, seeing it, recognizing it, knowing which way to attack it.
Now on the exam, are you wanting raw derivatives or you want
Well, again, we're still at a point where we aren't really doing anything with these derivatives yet, so the raw derivative is going to be the most important thing. I would rather give you more problems to do and ask you for raw derivatives than fewer and ask you to simplify at this point. But like I said, later on we will be working with the derivative and trying to, you know, set it equal to 0, and so we just you want to keep practicing what I told you, matching the back of the book with your answers. Yeah.
Are you going to do what you did on the last test and like take from the homework and quizzes?
Yes. The question is whether or not I'm going to like kind of take from the homework and quizzes for the next exam. Yes and no. I mean, the quiz that I just gave back to you, these problems, some of them were similar to the homework, some of them were a little bit, I don't know, a little more than the homework. I want to make sure you understand the concept. You know, that's the main thing, the concept of the product rule, the chain rule, how to distinguish between things. You know, like I just made up that problem right there, right? That to me is a fair problem on a test. So I wouldn't expect it to be like just like I'm going to take that problem and I'm going to go and I'm going to change numbers. Yeah. Okay. All right, implicit differentiation. Any questions over anything? I know you couldn't do all the homework, but anything that you in particular? No? All right, that's fine because I've got plenty to cover. All right, so let's take a look at this problem here. I'm working straight out of the book. This is actually number 21. They give you this equation, x squared plus y squared equals, and then in parentheses, 2x squared plus 2y squared minus x, all of that squared. And the instructions here are to find the equation of the tangent line at the point 0, 1/2. And they actually include the graph of this curve. And this is an implicit curve. Just so you know, remember from last class, the implicit equations that we had, they didn't have to pass the vertical line test, right? And this one, in fact, does not pass the vertical line test. It looks something like this. It's called a cardioid. Cardioid, yeah. I think I think it might come from this. I'd have to look at the... Okay, so look, we're going to the point 0, 1/2. So that means x coordinate is 0, y coordinate is 1/2. I have to assume that they're talking about this point because if I'm going to find the equation of a tangent line on a curve, then the point has to be on the curve. So I'm trying to find the equation, right? Not the slope, the equation of that line. So that's a little different. We've done this before. We have found equations of tangent lines before. It requires that we use that formula y minus y1 equals m times x minus x1. The m is the derivative, right? So I need the derivative, and that's what we're going to do. But I cannot solve this for y. But that's okay, because last class we learned how to differentiate things, right, without having to actually solve for the variable. So if I was going to try and find here dy dx, which for us has been y prime, right? That's what that's meant. Then I'm going to differentiate this implicitly with respect to which variable? With respect to x. So remember, we do the left side and right side separately? Okay, so let's take a look at the left side. The left side, we have the sum of two things. And when we take derivative of a sum, we just do derivative of each one separately. So the derivative of x squared with respect to x is just 2x. So I'm just start this here, 2x plus, now the derivative of y squared with respect to x. 2y and then times dy dx. Remember, because it's chain rule, right, the 2 drops out, 2 times y to the first power, and then times the derivative of this base of what was inside, which is dy dx. And that's it. That's the left side. We're done with the left. Equals, now on the right side, chain rule. What do you see?
Your hand with the square.
So you see something squared, right? Everyone see that? It's like something right here squared. The derivative of something squared, the 2 comes out, the something to the first power. So 2 comes out, the something, which I'm not even gonna touch it yet, right? I'm just gonna rewrite it to the first power. Then times, good, because that's chain rule. Now you can go inside and take the derivative, and it's all addition. So each one by one. So what's the derivative of 2x squared? 4x. And
4y and minus 1.
4x, close, plus 4y dy dx.
Y here.
And then minus 1. And then parentheses. Good. Okay, that's what I was just talking about, that parentheses. So this 4x came from the derivative of this, but because it's with respect to x, it's just 4x. This one, 4y dy dx, came from the chain rule. And then the minus 1, because again, we're differentiating x with respect to 1. With respect to x, it's 1, but there was a minus. And that's it, right? That's our derivative. And what I'm looking for is dy dx, and that appears right here. And it's over here, isn't it? Trapped in there. Now, in the problems we did last class, we would actually have to go and solve for dy dx, like isolate it, right? Get it by itself. But in this problem, I'm actually given the x and the y coordinate of where I'm interested in. So I could go solve for dy dx, but if I want to save myself a little time, I can just plug in 0 for x and 1/2 for y and just rewrite that and see what I get. All right, so let's do that. I'm plugging in x is going to be 0 and y is going to be 1/2, and then let me rewrite this. So 2 times 0, right? 0. I'll put it here, 0. Plus 2 times 1/2. 1 dy dx, so just dy dx, equals 2 parentheses 0 squared times 2, that's just a 0, right? So 0 here, plus, now be careful here, y squared. 1/2 squared is 1/4 times 2, 1/2. So that's 1/2. And then minus what? 0. And then over here, 4 times 0 is 0, and then 4 times 1/2, 2, so plus 2 dy dx, and then minus 1. And let me clean that up now. Any questions on that? That's just plugging in, right? So I'm at this point now where I have the left side is dy dx equals, and then this is just a 1/2, isn't it? It's just a 1/2.
Yeah.
And then times 2, which is 1. So that's just 1. I don't need to write that, right? It's 1 times something. So 1 times something is going to be itself. And then over here, what do we have? 2 dy dx minus 1. So I'm just going to write 2 dy dx minus 1. So that's your right side. We good with that? Yep. Let's solve for dy dx. So several ways you can do this. I have one of them right here, right? 1 dy dx here and 2 of them here. How about I subtract 1 from each side? Yep. Subtract one of those, subtract, and it'll just be a dy dx left over here, just one single one of them. Then I'd have over here, what, 0 and minus 1?
Pretty much.
And then add 1 to both sides. This is just like solving an equation for x, right? You're just isolating it.
So the derivative of that equation is 1.
The slope of the tangent line at that point is 1, right? This right here means dy dx is 1, which means for us the slope is 1, right? At that point. The important thing is we're only talking about one specific point. If somebody gave me a different x and a different y, then I would have a different slope. So you ready to write the equation of the tangent line? It's going to be y minus y1 equals m times x minus x1. So y minus 1/2 equals m, which was 1, times x minus 0. And solve for y. This is y minus 1/2 equals, the right side's just x. And just add 1/2 to both sides. So your final answer is y is equal to x plus 1/2. If you graph that line, it should be tangent to this curve at the point 0, 1/2 and have the slope of 1. Yes?
Yeah, how do you get from the top to 0 equals dy dx?
Okay, I subtracted one of these and subtracted one of them. This is 0. Two apples minus one apple is an apple. That makes sense? Because they're like terms. That's what I was saying. It's kind of like when you're solving for x. They're the same thing, so you can add and subtract both sides. Yeah. Yeah, this is if you want to, you could look at this equation. I'll use something other than x because we have x here. If we had this, and I ask you to solve for m, you'd subtract m from both sides, right, and add 1. It makes sense? I think one of these, that's like one of those kind of like light bulb things. Like as soon as you see it, you're like, okay, yeah. Are you there? Are you at that point? Okay. All right.
Maybe we could do one with like a Because I'm still a little confused on that.
Well, I have a good idea of what I'd like to do today. On Friday we did faculty interviews. Okay, we did interviews for faculty members that are wanting to work full time here, and I probably observed like 6 different people, like I think 6 different faculty members, and one of them had this technique that they're using in their class, and I want to try it today because I think it might be useful. Okay? So here's what I'm going to do. I'm going to put 2 and then x squared plus y squared squared equals 25 times x squared minus y squared. All right? And the point that I'm going to give you is the point 3, 1. And it's the same instructions. Find the equation of the tangent line, right? Normally what I would do is I'd say, hey, why don't you work on it on your own, okay? And y'all work in groups and see how it goes, right? Right? We're going to do it this way. You're going to be in groups, but you're going to be on the board, okay? So you need to make a group of 3 to 4 students in a group. If you want to do a pair, that's okay. But every group needs to take a section of the board. You'll need to talk to each other. You need to work this problem out on the board. Everybody. So we use that board. I think we can probably get 2 groups on that board. 1 group here, 1 on each side here. I have markers here. I am going to mute the microphone, all right, so this isn't recorded. understand that there is value in studying in groups, okay? Getting together with classmates, getting on boards and working together. Because you can bounce things off each other. Someone's going to know something you don't. You can help clarify something. When you do that, when you help someone else, it just solidifies it in your own mind. I'll try from now on, whenever we have an in-class, like let's let you try it. Let's do this method, okay? We just can't do it all the time, all right? And the rule will be, the next time, whoever was writing cannot be the person who writes. So whoever was the scripter today cannot be the scripter next time, all right? I just don't want to have like one person just sitting there like watching going, you know, the whole time. Just nodding the whole time. What's good about this method, what I really like about it is it's very easy for me to look around and see what's going on. And like who's getting and what the conversations are. All right, well, let's not erase all this right now. All right. Next problem. Let's take a look at x to the fourth plus y to the fourth equals 64. I want us to find y double prime. Now remember, there was a time when we were talking about derivatives that we talked about, hey, you can have a first derivative, a second derivative, a third derivative, right? There's really no limit to how many derivatives you can take. So for this one, let's find y double prime. Now when we do this, I'm going to change the notation just slightly, all right? Let me make sure the camera still has me on here. Yes, we want to all understand that when we write y prime, that what we mean is dy dx. And when I write y double prime, that means the derivative of the derivative, right? It's the derivative of the derivative. And there was a Leibniz notation for this. Do you remember? It was something like, they put like a 2 and then the 2 here, and they were offset 2s so that you wouldn't think it was squared. We're not going to use this notation at all right? I just want everyone to understand the y double prime will mean the derivative of the derivative, and the derivative we are talking about dy dx. Why is it important for me to tell you that what I mean by y prime is dy dx? Why is that important? That's right. I guess what I'm getting at is, what was the problem with this notation that we learned last class? That's right. You don't know with respect to what variable, right? We assume that it's with respect to x, which I'm telling you, yes, it is. All right? We are going to differentiate with respect to x. Okay, here we go. I'm going to just differentiate left and right hand side. So the derivative of the left side is with respect to x, 4x cubed, and there's nothing fancy there, right? 4y cubed times dy dx. That's it. Okay, so there's your chain rule. And then equals 0. Now, I said I was going to use slightly different notation, right? So here we go. I'm just going to write this. I think you would all agree, hopefully, that that's the exact same thing.
Yeah.
I'm just using a different notation. Instead of dy dx, I'm writing y prime.
That's real hard to write it.
Yeah. All right. Now, I could right now solve this for y prime, couldn't I? I could take this term to the other side and then divide through by 4y cubed, and I would have y prime isolated. And I'd be done if that's what I wanted, but I want the second derivative, right? So what I'm going to do right now is keep in mind that I can solve for y prime, but because I'm trying to get y double prime, I'm going to take the derivative again right now. Just right now, as it appears, take the derivative again. So what's the derivative of 4x cubed? 12x squared. Good. Plus, dun, dun, dun. Good, you have product rule. Y'all see the product? It's right here. You have this thing times this thing, right? So I'm going to first do, well, product rule is the derivative of the first times the second plus the derivative of the second times the first, blah, 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 blah. All right, derivative of the first one is 12y squared dy dx. Because you have to do chain rule on that, wouldn't you? Because I'm differentiating with respect to x. So this would be 12y squared dy dx. But I'm going to put instead of dy dx, y prime. Is that okay? That's the derivative of the first one. Times what? The second one, which is y prime again. So times y prime. This is not y double prime. This is not the second derivative. This is the first derivative times itself again. Times, right? Not this. It's not the derivative of the derivative.
How did you get y prime?
Which one?
The second one.
Product rule. Derivative of this is this piece right here, right? Times the second one, right? We were doing like f prime g plus g prime f, right? That's the product rule. F prime is here times g plus now g prime, which is the derivative of this one. Understand? What's the derivative of the derivative? That's your second derivative. That's what we're trying to solve for. So this is y, I'll put y prime prime just so you can see. I'm doing the derivative of this one, the derivative of that one. Am I done? Times what? 4y cubed. And that finishes off the product rule. I'm going to just put brackets here. That's this, 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 this. So this piece right here is like f prime times this is g, plus this is like g prime, and then this is f.
Do you need parentheses around all that?
Which part? All of this?
After the plus sign?
Here?
No, the first plus sign.
Here on all that? In this case, I would not, and the reason why is because this is not multiplication. See, when if I were saying this times this, right, I would need that all in parentheses. But I'm saying this plus this. See the difference? And you can go back to like just a basic example. If I say 5 plus 4 plus 3 versus 5 plus parentheses 4 plus 3, you're going to get the same answers, right? Change that to multiply, totally different answers. All right, we good? Equals, right? Still need equals. Equals what? 0. Derivative of the right side is 0. All right, I'm going to try and clean that up. Here's what I have. I have 12x squared plus 12y squared, and then y prime times y prime, which I'm going to write as y prime squared. Because that's what it is, right? It's not y double prime, it's y prime times itself, y prime squared. Plus y double prime, and then times 4y cubed, and then equals 0. There we go. May I erase this stuff over here? Okay. I am also going to rewrite this piece. I'm going to rewrite it right up here just so I have it. I'm going to kind of box that up here. That was when I took my first implicit differentiation. Here's what I get when I took it the second time. Now this problem doesn't ask for y triple prime, right? But if it wanted, I would just do the derivative again on this. I'm trying to find y double prime, so I need to isolate. I need to isolate this piece right here. I'm going to try and isolate it. You ready? So let's bring all the crap on the left side that does not have y double prime in it and bring it to the right side. So it'll be something like this. Y double prime times 4y cubed equals negative 12x squared minus 12y squared, and then y prime squared. Agreed? I just brought this one and this one to the right side. What else could I do? Divide by 4y cubed. So divide this side by 4y cubed. Divide this entire side by 4y cubed. And I'm going to be pretty close to a final answer here. I'm going to have y double prime equals negative 12x squared minus 12y squared times y prime squared over 4y cubed. Yeah, you could reduce some stuff out, which I'll do in a second. But let me ask you something. Last class, when we were finding the derivatives implicitly, we said, hey, these are not functions like the circle. And we said, to find the slope of the tangent line, I'm going to need to know more than just x, right? I'm actually going to need to know what? X and y, right? I need the exact point to be able to tell you where the slope of tangent line, what the slope of tangent line is going to be. Here, what we're saying is that to know the second derivative, I'm going to need to know what? The x and the y and the slope of the tangent line at that point. That's a lot of information to have to know, right? To know the second derivative. So what I'm going to try and do right now is I'm going to try and rewrite this so that it just has x and y, no more, like no derivatives in it at all. And the reason why I feel like I can do that is because I can take this equation and solve for y prime, can't I? And then I can replace it in here. And then everything should be x's and y's if I do that. All right, so let's do it. Let's take this, solve that for y prime real quick. It'll become 4y cubed y prime equals negative 4x cubed. Do y'all agree with that? Just moving the 4x cubed to the right side. Divide both sides through by 4y cubed. Y'all still agree? Yep. And this just becomes negative x cubed over y cubed. The 4's go away. You'll still have a negative 1 on top, but the 4's are gone. Oh, I should not have written that. That's bad notation. Sorry. I should write like a little arrow and tell you that the left side is y prime, the right side is negative x cubed over y cubed. I still need my y prime on the left side. So it's an equation. This is this. Now I'm going to take y prime, and this right here, I'm going to stick it right there. And I'll do that right here. I know somebody in the back of the mind is asking themselves, like, will you take this as the answer on the test, right? That's what you're going to ask. And I'm going to tell you no. I want it completely simplified. So I will give you the instructions. Find y double prime in terms of x and y. So I want it in terms of x and y at the end of the day. So let's plug in. Y double prime is equal to negative 12x squared minus 12y squared. And then I'm going to plug in here for y prime the fraction negative x cubed over y cubed, but that's squared, isn't it? Yeah, we'll talk about what we do there in a second, but that's all over 4y cubed. Yeah, what do you do when you have a fraction squared? Square top and bottom separately, and then when you do this one, when you square this thing, let's say that negative is with it, right? Negative 1 on top. You square the negative 1, so it becomes positive. X to what power? X to the 6th. So we have this now. Y double prime equals negative 12x squared minus 12y cubed, and then you square the top and it becomes x to the 6th, and you square the bottom, it becomes y to the 6th. That's all over 4y cubed. Yes?
What did the 12y cubed? Yeah, mine's still squared.
Was it squared? Oh yeah, I don't know where I did that. Was that squared? Yes. That should be back here too, right? Mm-hmm. Okay, thank you for pointing that out. It is squared, right?
I've been writing it squared.
Yeah. This is cubed, right? Yes. Okay. All right, so I'm just going to try a couple of things here. I noticed that when I do this multiplication, this is like on top y squared, this is below it, it's y to the 6th, so I can clean that up, right? Cancel out, and that should leave me with a y to the 4th on the bottom. So negative 12x squared minus 12x x to the 6th over y to the 4th all over 4y cubed. We still good?
No, get rid of the freaking 12.
Oh, you've been wanting me to do that for a while, haven't you? All right, since this has a factor of 4, that has a factor of 4, that has a factor of 4, I'll reduce everything by a factor of 4. That's fine? No, it's fine with me. So it'll be what, negative 3x squared minus 3x to the 6th over y to the 4th, and then over 4y cubed. Over, yeah. Sorry. Good question.
No, yeah.
I mean, you have it in terms of x and y, don't you?
Yeah.
So one could argue that you're done. Yes, one could argue. But if you look in the back of the book, it's not going to have this. So watch what I do right now, okay? You ready? The numerator is a complex fraction, right? It's a fraction. We've got a bigger fraction. Let's get a common denominator between these two and put them together. All right? So what would the common denominator be? Y to the 4th. So I'm going to look at that as over 1, right? So when I put a y to the 4th, I have to do it on top and bottom here. I will get a negative 3 x squared y to the 4th minus the other numerator, which I didn't have to do anything, right? So minus 3x to the 6th over, what's my common? Y to the 4th, and then what's underneath that? Y to the 3rd.
Now you flip up the thing.
You want, oh no, I'm not looking at you. Sorry. You're good? You want to go walk around outside or something? You sure? You want to finish it up for me? Okay, all right. All right, so over 1. And watch what I'm doing. I'm just going to bring this and flip it like that, right? And so I'm going to get this y cubed is going to be on the bottom and go across, and that's going to be a y to the 7th. Y'all okay with that? All right. Something really good is actually about to happen, all right? Believe it or not. Look at my numerator and tell me about a GCF. Can you see a GCF in the numerator? Negative 3 x squared. Okay, let's pull that out. Negative 3x squared, right? And then when I pull that out, what am I left with? Y to the 4th, not minus, we pull the negative out, plus x to the 4th over y to the 7th. Does anybody see what I'm about to do? No, this one's kind of hard to see until I show you the first time. What is x to the 4th plus y to the 4th? It's 64. Because the original problem is presented this way, right? In this problem, it is, you were told from the beginning, x to the 4th plus y to the 4th must be 64, right? That has to be true. And then we work all the problem out. So if later on we see x to the 4th plus y to the 4th, guess what? That still has to be 64, doesn't it? So I can replace all of this with 64. All of this. And so this becomes y double prime equals negative 3x squared times 64 over y to the 7th, and then that's, what's 180, negative 192 x squared over y to the 7th. That is pretty clean right there.
I'm just telling you right now, I'm not going to be able to get that on the test.
You will if you're ready. You will if you're ready for it. Numbers 25, 26, 27, and 28 out of the homework set are all like this. Okay? Be ready for that. Finding y double prime with implicit differentiation, these problems are a little messy, all right? As you can see. But that's fair game. You can do it. You can't go into it looking at it like I can't do that. You can do it. Well, you're capable of it. It did. That was a while, huh? All right. Let's see if there's anything else out of this. I believe I'm happy. Related rates. I want to give you an introduction today. We will do the full-blown related rates next class, but I'm giving myself about 30 minutes, 40 minutes here to try and get us to start thinking a certain way. All right, so this is the problem that I decided I was going to use to start this off. Huh? Yeah, let me write this down. This is going to be intro to 2.7 related rates. The idea here is that in the real world we have equations all over the place, right? That usually relate things together. I think we did this one last class. Do you remember us talking about this one? We did this one, right? It was a chemistry formula. Pressure, volume, number of moles, Avogadro's number, something like that, temperature. But all over the place, there are equations relating quantities together. And what we're interested in is trying to find out how the variables are connected to each other. But not in the sense of algebra. Like in terms of algebra here, if P were to go up here, right? If the pressure were to go up, that means this side of the equation must get bigger, right? Right? This is going to become larger. And the only way to maintain balance is to make your temperature go up, right? So if P goes up, then T must go up, right? If the volume goes down, then what must happen? The temperature must go down, right? This is not what this section is about, okay? Related rates is not about the relationship between one going up, the other goes up, or one goes down, the other one goes down. This is about how fast they do that, right? So let's say that the pressure is going up at a certain rate. So I'm applying pressure into the container at a certain rate. The question is, how fast is the temperature going up, right? So increase the pressure, temperature goes up. But if I tell you how fast I'm doing this, I want to know how fast this goes up. And what we're going to find is that in a lot of real-world situations, the way that they're related to each other is not linear. Meaning, if I increase the pressure by 1, the temperature doesn't go up by 1. A lot of times the relationship is nonlinear. So related rates means the relationship between the rates at which things change. The first example I'm going to do is visual, and I'm going to use this ruler, all right? So let's say that we have a wall. This is a classic example, okay? This is used a lot in calculus classes. Okay, we have a wall and we have the ground. And this ruler represents a ladder. Okay, so I have a ladder right here. And I put the ladder here up against the wall. And let's just say, if I can hold it without it going anywhere. There's my ladder. And let's just say that it's a 12-foot ladder. Right? So that's the point at which it touches up there, and that's the point at which it touches down there. Now, if I take the bottom of this ladder and I start pulling the bottom of the ladder out this way, should we put a guy up there? We'll put a little guy up there. All right. You're supposed to be spotting that guy. All right. I guess he only has 1 foot on the ladder anyway. So I'm supposed to be holding the ladder, but I decide, you know what? He needs workers' comp, so I'm going to pull the ladder out from him like this, right? and I'm going to pull the ladder out at a constant rate. So think about this point right here. I'm going to pull it. Now, if a point is moving, it has speed, right? And I'm telling you that the speed at which I'm pulling the point out is constant. So maybe I'm pulling it out at 1 foot per second, right? 1 foot every second is how fast I'm pulling the bottom of the ladder out. The question is, how fast is he coming down? So let me try and do this off camera. Here's the wall. All right, can you all see that? He's up on this ladder. If I start pulling this out at a constant rate, then did he come down at a constant rate?
Yep. No. Oh, no?
No? What do you think happens?
Gravity.
What do you think happens? Does he go slower and then speed up, or does he speed up and then slow down? Okay, slower and speeds up. Slower and speeds up? Okay. So when maybe if I do it here, if I get it almost vertical, you can well, I still need to be up against something. If I go almost vertical, just watch the point at the top here. Okay, watch how fast it's moving down the wall. I'm going to try and come off of here as even as possible. Do you see that? I tried to pull out at a constant rate. Initially, that point didn't come down very fast, right? But as I got further out, that point started coming down faster and faster. Do you agree? Okay. So what we're going to be asking ourselves is, if this is coming out, if this point is coming out at 1 foot per second, so I'm giving you a rate, right? This is a speed. That's a speed, feet per second. That's how fast that point's coming out. The question is, how fast is this coming down, right? Feet per second. And what we just determined, just from the visual, is how fast it comes down actually depends on where it is, right? It depends on, are you talking about how fast was he coming down here? Or were you talking about how fast was he coming down when he was right here screaming for his life, right? That's a scream. All right, so this point matters, doesn't it? All right, any questions? I'm going to start putting this information down now, writing it down technically, all right, in a more technical manner. We have a 12